Welcome to the Big Picture podcast. We're going to start digging into the latter half of the nuclear chapter with a focus on nuclear fission and fusion, which sound a lot alike but are not the same thing.
Okay, so where do you want to begin?
Well, let's start with a definition. What is nuclear fission?
Fission is usually when you break things apart.
Yeah, and the term was borrowed from biology. Rather than calling it cellular fission, they called this nuclear fission. And so that's a division of the atomic nucleus.
So the splitting of atomic nuclei.
Yeah, splitting the atom.
Okay.
Now, here's an important distinction. We've been talking about radioactivity. That's like a nucleus losing an electron or losing an alpha particle. The atom is not splitting in half. When we talk about nuclear fission, we're talking about the nucleus actually splitting in two large fragments, like it's splitting in half. That's the distinction between nuclear fission and plain old nuclear radioactivity.
Sounds good.
What are you doing? Oh. Here are the main points. Not every nucleus is susceptible to fission. In fact, there are only like 3 isotopes that are susceptible to nuclear fission. They are uranium-235, plutonium-239, and uranium-233. But it works like this. You might think of a large nucleus hard as a bowling ball. It's not. A better analogy is to think of it like a big ball of taffy. And what can happen is if you shoot a neutron, just a neutral neutron, toward that nucleus, like a big ball of taffy, it elongates, right? What was once a beautiful sphere turns into this oblong thing. Now, can you think of any issues that might arise when suddenly you're stretching out an atomic nucleus?
The distance is going to affect the strong nuclear force.
So if you're protons on opposite sides of that elongation, think about what that elongation does to the attraction you have for each other.
It's going to decrease the attraction. Then the electric force is going to have a greater influence on it.
Yeah, the electric force is going to suddenly win out. Remember, it's a battle between the electric force of repulsion and the strong nuclear force of attraction. And so if you have a nucleus that's able to bend out like a ball of taffy when hit by a neutron, you're going to find what happens is it splits apart. And why is it split apart? It splits apart because of the electrical force of repulsion. It splits apart because the nucleus has elongated and the strong nuclear force from nucleons on the opposite sides weakens quickly because you know distance is key when it comes to the strong nuclear force. And then you have 2 positively charged nuclei next to each other, and they themselves scram away from each other as fast as possible. And it turns out when it divides like that, it's not typically a clean division. Like half of it goes here and half of it goes there. There are neutrons that are scattered and alpha particles that are scattered, beta particles that are scattered about. I did mention neutrons, didn't I?
Yeah, wasn't it the neutron that was splitting it apart?
One neutron goes in, splits it apart. And because it's not a clean division, you can have like 3 neutrons come out. So 1 neutron goes in, 3 neutrons go out. And guess what those 3 neutrons coming out can then do?
Well, then they turn into protons.
They would. But if it's quick enough,
they can hit other uranium nuclei.
Yeah. And so 1 neutron goes in, splits a uranium nucleus, and out come 3 additional neutrons. Any one of those neutrons can hit another uranium, which would generate 3 more. So 1 begets 3, which begets 9.
It's a chain reaction.
Which begets 27, which begets whatever. And yeah, we call that a chain reaction. Here's the key. We're assuming you've got 100% uranium-235. In nature, there's not much uranium-235 at all. Mostly in nature, what you've got is its milder cousin, uranium-238. It's like out of every 140 uranium atoms, only one of them is uranium-235. Uranium-238 is not fissionable. It has a balance of protons to neutrons that make it more stable than the uranium-235. So we don't have much uranium-235 out there. It's mostly uranium-238. So how are you going to build a nuclear bomb?
Well, is that what is meant by enriching uranium? They
Yes.
have plants to enrich the uranium from 238 to 235.
Yeah. What you need to do is enrich the uranium-235. That is, make it more concentrated. And here's the big problem. How are you going to separate uranium-235 from uranium-238? They're both uranium. They're the same thing. You're trying to separate the same thing from the same thing. In chemistry, when we try to isolate something, we take advantage of the differences in physical or chemical properties between the two substances. Now, the uranium-235 and 238, they have the same chemical properties because they're both uranium. The only way they are different is that the uranium-235 is a little bit lighter, but not by much.
And so you really have to find one out of every 140 uranium atoms?
Yeah.
Wow.
And you react the uranium with fluorine, and you make a uranium hexafluoride, which is a gas. So you essentially gasify it, and then you put it in these big centrifuges, and you spin it. You spin the gas round and round. And what happens is the heavier uranium-238 goes to the outside, and the uranium-235 stays in the inside. And then you blow that concentrated uranium-235 into another chamber, and you do the whole thing again. And then you blow into yet another chamber, and another chamber. And each time you do that, you get less and less material, you see, which makes sense because there's not much of the uranium-235 in there to begin with. But you do that through a series of centrifuges. So maybe you'll hear about that in the news, maybe like with Iran, and they're trying to concentrate uranium-235. Nuclear regulatory powers on this planet are wanting to prevent them from doing that. That means minimizing the number of centrifuges they have on hand. Because the more centrifuges you have, the more uranium-235 you can generate. But you don't need to get to 100% in order to have a bomb-grade material. You can do it with much lower percentages.
I know, I just wonder if we are now on the radar for national security.
How to make the bomb is well known. It's the technical hurdles, the engineering, that thankfully is the major obstacle. Let's forget all this talk about bombs, okay? If you have uranium enriched just to 3%, turns out you're going to have some chain reactions going on within that lump of 3% uranium-235. And what you can do is if you have a lump of uranium that's 3%, you know it's not going to blow up like a nuclear bomb. It's just not concentrated enough. But there's enough chain reaction going on in there that it's hot, quite hot. You don't want to hold it in your hand. So what you do is you drop it into a bucket of water. Normally when you throw like hot rock into water, the rock just cools down quickly and the water heats up. Make sense?
Mm-hmm.
Take a lump of uranium that's enriched in just 3% uranium-235. You throw that into the water, it's going to heat up the water, but the lump of uranium never cools down.
Whoa.
It stays hot. And the reason it stays hot is because there's nuclear fission reactions going on within that 3% uranium-235.
Okay, but after 1,000 years or so?
No, after 3 years.
Okay.
3 years. Yeah, what happens there is after a year, you're not at 3% uranium-235. You're at 2% uranium-235.
Oh.
And then you go to 1% uranium-235. And you know what? It just doesn't heat the water up quite as nicely.
Okay, so then you probably want to get new.
You
They're
want
called
to
rods,
you want
aren't
to fresh
they?
it up. Yeah. So in a nuclear power plant, that's how it works. We just described how a nuclear power plant works. You throw a lump of uranium-235, a 3%.
Or a rod, right? They call them
rod.
rods.
Yeah, they have
right?
rods. You can look all that up. But the main idea is that you're exposing 3% uranium-235 to water, and it heats up the water. The water turns into steam. The steam rises and turns a turbine, which generates electricity. A nuclear power plant and a coal-fired power plant operate by the same principle of getting water to boil, to turn into steam, which turns a turbine, which generates electricity that we use to turn on our lights.
Because it's moving magnets across each other.
Yeah, excellent. Now, the difference is the source of energy. For a coal-fired power plant, which, by the way, is emitting lots of radioactive particles that are inherently within the coal into our atmosphere, the source of energy is the burning of the coal, the combustion of the coal, which, by the way, generates a lot of carbon dioxide, which is not helpful to the climate.
Okay, but we know that there is still an issue with nuclear power reactors.
Okay, let's go into where that issue is. So,
what do you do with those rods when they're not heating up the water the way you want them to?
Yeah, so it's
Now what do you
got
do?
to 1%, and it just doesn't heat up the water as efficiently. What you need to do is you got to shut down the entire plant, pull out those 1% rods, and put them somewhere.
For a long,
For
long
and whose
time.
backyard? It's not just the uranium. Remember, the uranium has a very long half-life, so it's not that dangerous. But when you split here, this is really cool. Get this: when you split a uranium nucleus, right? You're making two smaller nuclei. We call them daughter nuclei. Now, what do you know about heavy nuclei?
They're not so stable.
They need a lot of neutrons, don't they? Because they're so unstable, you need a lot of neutrons, right?
Mm-hmm.
But smaller nuclei don't need those extra neutrons. So get this, when you split a uranium atom into a smaller nucleus, it has all these extra neutrons. And the nucleus is going, but I don't need all these extra neutrons because I don't have that many protons anymore. What you end up with is a daughter isotope that's really radioactive. And that is not a problem.
What?
It's not a problem. All you have to do is put it in the back of the plant, and within a week, it's no longer there. Yeah, put it in a pool of water, put it in a cement it maybe in some glass, and it's no longer there. It's not a problem. What is a problem is that there are daughter isotopes that have half-lives on the order of 10,000 years. That's not good, because it's not going to just bloom, bloom real quickly in front of you, but it's going to still be very radioactive. 10,000 years is much more radioactive than 4 billion. A half-life of 10,000 years is much more radioactive than a half-life of 4 billion years. So what are you going to do with this material for 10,000 years? And beyond 10,000 years, because after 10,000 years, you have half of what you had. You got another 10,000 years, then it's a fourth of what you had. So we're talking 100,000 years, then you're okay. Where are you going to put this stuff for 100,000 years?
There is nowhere that you can safely put such highly radioactive materials anywhere.
It's a problem. The students will ask, well, why don't you just send it up into outer space?
That's sort of interesting.
Yeah, why don't you just send it up to outer space?
Send it back to where it came from.
No, it came from, originally, way back when. Two problems with that. One, we hope there's no accident as the rocket is going up into outer space. And two, the sheer number of tons of this stuff we now have, millions and millions of tons of this, you can't get all that into outer space with present-day technology. It's not practical.
So now we're just really stuck with this on our Earth, affecting all living organisms.
We want it contained, right?
There is no safe place to contain it.
Safety is a relative thing now, isn't it? We talk about the risk factors, the risk-benefit ratio and all that. And these are important questions for us to consider. Is it worth going forward with this nuclear fuel?
No.
When it emits zero carbon dioxide? How are we going to supply energy to modern civilization?
There are plenty of ways.
There are plenty of ways. We've got to work on those. But what are we going to be doing in the next 5, 10, 15 years, 20 years out? It takes time for those technologies to get on board. Yet we're growing so fast.
We could do it.
All right. I'm for it. I'm for it.
It can be done. I think this is just, I mean, I'm sure, I have no doubt that we could take care of our energy needs in other ways and not be stuck with this tons and tons of toxic material. I have a question. I wonder if at some point, maybe someday, this material, somebody will actually figure out a use for it.
Oh, absolutely. Are you ready?
Yeah.
A lot of that material contains uranium-238. Remember, it's only 3% uranium-235. It's got a lot of uranium-238 still in it. Mm-hmm. So when you're storing it away at Yucca Mountain or in somebody else's backyard, it's really radioactive, that's true. But it's also got a lot of uranium-238. And you can take uranium-238 and transform it into plutonium-239. You can use that as more nuclear fuel for plutonium-based power plants, nuclear power plants. Because guess what we're running out of?
You can't say uranium.
Uranium. You know, North America's already depleted its primary aluminum ores. The United States now gets it primarily from Australia at this point. I mean, we are impacting the planet. We're running out of high-quality uranium ore. We've mined it all. Yeah. And so now we have all that uranium sitting in these containers next to the power plant. So what about that? You could take the uranium-238 and transmute it to plutonium-239.
And then that would also heat up water and act in a reactor.
Yeah. You can make a plutonium-based power plant just as you can make a uranium-based power plant. In France, interestingly enough, about 70% of their electricity comes from nuclear power plants. And they have a type of power plant called a breeder nuclear power plant, where you put in the uranium and you use that as a fuel, but then it transforms into plutonium-239, which you use again as a fuel. So it's like a fuel begetting a fuel. An issue with those types of breeder reactors is that it's fairly easy to develop nuclear bombs from them. And so for security reasons, we focus primarily on the uranium-235 nuclear reactors. You know where I'm going next, don't you? Mm-hmm. We can sidestep all of this by forgetting about plutonium-239 and uranium-235 and instead focusing on that third isotope that can undergo fission, which is, wait for it, uranium-233. You're giving me a weird look. Uranium-233, as everyone knows, is created from thorium. I'm late. I overslept. Thorium. Didn't I talk about thorium earlier?
Yeah, we were going to talk about thorium reactors.
We're here. We're finally here. Thorium reactors. There's 4 times as much thorium on this planet than there's uranium. Thorium is abundant. Now what you do is you take thorium-232 to a neutron and it transmutes into thorium-233, which beta decays into
uranium-233.
Uranium-233, that's it. And uranium-233 is that third isotope that can undergo nuclear fission. Without going too much into the technology here, you can create a reactor that uses uranium-233 instead. And it operates at much lower temperatures. You can have a much smaller nuclear reactor. And the byproducts of the reactor itself have half-lives that are no longer than cesium-137, which requires only like decades for safe storage because its half-life is much, much shorter than the products of, say, uranium and plutonium reactors.
Okay, so with a shorter half-life, it's going to be more radioactive, so a little bit more dangerous.
But it doesn't hang around as long. The half-life of the byproducts of the thorium reactors, you just need to store it for like decades, as opposed to millennia. And that issue is that during the transmutations, you also generate thallium-208 isotope, which emits gamma rays really well. And they tried to make a nuclear bomb out of the 233, but there was all this thallium-208, and it's a gamma emitter, and it simply fried the electronics. Just made the nuclear bomb testy. It didn't work very well. And because you couldn't make a good nuclear bomb out of the uranium-233 coming from the thorium, they stopped the research.
Oh, really?
Yeah, that's my understanding. But it's coming back, slowly but surely.
Where is it coming back?
There are a few private companies in the United States. You've got China, you've got the UK, you've got India, all sponsoring research into the thorium reactors.
And so the
thallium-208?
The thallium-208, is that also very radioactive and dangerous?
It's dangerous, yeah, because it's a gamma ray emitter. And as it's produced within the reactor, what you do is nothing. You just leave it in there, and the energy it's producing helps to generate the energy.
And can it fry the reactor?
Nope, you're not going to have circuitry. The reactor operates in a liquid phase at only about 300-400 degrees, as opposed to hundreds and hundreds of degrees. And it's a liquid, and because it's a liquid, the fluid itself, the reacting fluid itself, can be the source of heat, of heating up the water to create steam. As a liquid and not getting super hot, you're just not going to have large explosions. And guess what? As it gets hotter, it shuts itself down. Kind of like you're on a sailboat and you let go of the sail, the boom, any sailors out there, the sailboat immediately goes upwind and slows down. Just let go of everything. That's called a passive safety mechanism. And so if it gets too hot inside the nuclear reactor, what happens is the thorium stops producing 233. The thorium starts producing other isotopes of uranium that don't undergo fission, which means
it stops.
It stops.
Okay.
If it gets too hot, it stops. Another thing you can do is you can put a plug underneath this big hot liquid, and if it gets too hot, the plug melts and outpours the liquid into a container to cool back down. You can build these on small scales or a bunch of them lined up on larger scales. They don't produce carbon dioxide. You're able to remove the products from it while it's running. You don't have to shut the whole plant down in order to clean it up. You can remove the byproducts by distillation or electrolysis during the operation of the plant. That's the thing about like a uranium plant. You got to shut it down for a fair amount of time in order to remove those 1% rods. So there are all sorts of technical advantages to using and economical advantages to using thorium as your basic fuel for the thorium-based reactor.
Yeah.
All I'm saying is check it out. Do a web search on thorium reactors, the LFTR, the liquid fluoride thorium reactor, and you're going to get a lot of very interesting information.
Okay.
Yeah. We're about to jump into E equals mc squared. Energy and mass are the same thing, like one mouth that can either smile or frown.
So when you say equal, you mean the same thing.
And that's what we mean by equal. It's a relationship, and this equals that. This is the same as that. E equals mc squared is telling us energy is the same as mass times the speed of light squared. The two can interconvert.
That is very cool. Let's talk about this.
That was the Einstein thing. We're going to do a little mind exercise here. In my left hand, I've got a 1 kilogram magnet. And in my right hand, I've got another 1 kilogram magnet. See that? Mm-hmm. All right. What's the total mass?
In both hands, you have 2 kilograms.
2.0.
Okay.
Kilograms.
2.0.
0 kilograms. Now, if I bring them together, are they just going to come together like 2 styrofoam blocks? Or because they're magnets, might it be a little different?
As they get closer, they're going to be attracted together.
Yeah, they're going to come together like that. They're going to accelerate toward one another. And as they accelerate, you've got an increase in kinetic energy, right? And they hit, and heat is released. Once they're together, go ahead and put that on an ultra-precise balance, and guess what the mass will be? More than 2.0, 2.0, or less than 2.0?
All right. Well, you just said that heat was released, so I'm going to actually guess that it's less than 2.0.
Because you recognize the heat, the energy release, kinetic energy, heat energy, light energy, all that energy that was released came from somewhere. It came ultimately from the conversion of some of that mass. I'm going to exaggerate the numbers here. You put them together, it all adds up to 1.8 kilograms. So a 1 kilogram magnet and a 1 kilogram magnet apart, that adds up to 2 kilograms. But let them come together, it now has a mass of 1.8 kilograms. And you're like, well, where did that 0.2 kilograms go? Answer?
Into heat.
Energy was released. Yeah. It all adds up to 2 kilograms, but 0.2 kilograms was transformed into energy. Here's a case where the mass was converted to energy. Now, the numbers I used there just are exaggerated. It's not to that extent. But
right.
Let's do the reverse.
Wait, I want to ask a question first.
Yeah. What?
So if you take them apart again, I know you said let's do the reverse, so you're about to do this.
Yeah.
But will you still wind up with 1 kilogram in each hand?
Let's have 2 magnets together, and the total mass is, say, 1.8 kilograms. And what you're going to do is pull them apart. Here, let me give them to you. Okay, you got it? All right.
Got it.
Now go ahead and try to pull those 2 magnets apart.
They're really sticking. They're really,
it's hard, isn't
really
it?
stuck.
It's hard. They're
okay,
really strong magnets.
Got it.
You got it. Okay, now they're apart. How do you feel?
Tired?
Tired, yeah. Do you recognize it required energy from you to pull them apart?
Yes, for sure.
Guess where that energy went?
Back into the mass of the magnet?
Yes, back into the mass of the magnet. Yeah.
That's crazy.
The magnets aren't just going to come apart from each other on their own. You got to put in energy to pull them apart. And guess what? It's the same amount of energy that was released when they came together.
That makes sense.
Adds up. Yeah, there's a lot of energy conservation there. So for magnets, the forces aren't much, and so it's totally not noticeable. But when we get to the world of the nucleus, it is noticeable. And the evidence has been before you through this whole time. Whenever you look at a periodic table, look to the mass of hydrogen in the periodic table. Okay, what do you see there? Mass of hydrogen.
1.0079.
All right. How do you make a helium atom?
You take 2 hydrogens together.
And?
You have to squish them together.
2 protons and 2 neutrons.
And 2 electrons.
And 2 electrons, yep. Give you a helium atom.
Mm-hmm.
So for argument's sake, let's say that protons and neutrons have the same mass. They don't, but it's close enough. So essentially, hydrogen is 1.0079.
Oh, 1.0079.
Multiplied by that by 4, you should get the mass of a helium atom. So 4.032 should be the mass of a helium atom, right?
Correct.
Yeah, because you're just taking 4 of those nucleons and putting them together.
Right.
You ready? Look to the periodic table. What do you see for helium? What's its mass?
Its mass is 4.003.
That's less.
That's definitely less.
That's way less, actually. You see? What's happened here, you're taking those 4 nucleons, 2 protons, 2 neutrons, putting them together to make helium. You might expect mass to be conserved, and you look to the periodic table and you see that it's not.
Oh, so wait. If it's lost, then they actually wanted to go together. Like it released energy.
When they went together, you got less mass. And the reason you got less mass is because what was released?
Energy.
Energy, yeah. So that's the analogy we were using with the magnets. It's the same thing when you look to the elements of the periodic table. Is that cool or what?
That is very cool. I'm going to have to think about this for a while.
Yeah, go back to the magnets. I find that really helpful, is that when you bring them together, they accelerate and energy is released. You feel it's warmer. That means it's going to be lighter. When you try to pull them apart, it requires energy to do that. And that energy is being transformed into the added mass. Take 4 nucleons, scrunch them together to create a helium atom, and you're going to find the total mass is less because energy is released. You're bringing together these nuclei, and we call that nuclear, not fission, but nuclear
fusion.
Fusion.
You're fusing it together.
Yeah. Yep. Now, there's a real important graph. We like to call it the most important graph in the entire universe.
So the y-axis is mass per nucleon.
Okay, let's think about that. Mass per nucleon. It's how much mass a nucleon has. You might think a neutron is a neutron is a neutron. Well, it's not. The mass of a neutron depends upon where it is. If the neutron is in a helium atom, it's got less mass. And we saw that in the periodic table. If the neutron is in a hydrogen atom, it's going to have more mass. So not all neutrons have the same mass. The mass of a neutron depends upon where it is. Same thing with a proton. Now, that y-axis you said was mass per nucleon. And what that means is how much mass a nucleon has.
Okay, and then the x-axis is the atomic number.
Which is
the number of protons.
Yeah. Okay. Now for our podcast audience, describe the curve on this graph plotting mass per nucleon and atomic number.
All right, I'll give it a shot. So the curve starts with a higher mass per nucleon, so a high nucleon mass.
So it's moving left to right. It starts really high.
Starts really high, and then it quickly drops, even at low atomic numbers.
Yeah.
And then it starts to increase very slowly as the atomic...
it curves about right there and then starts going back upward.
Right, and the mass of the nucleon will increase as the atomic number gets larger. No, it's very slow, a gradual curve.
After that quick drop.
So a quick drop and then a gradual increase.
Yeah, it's like... How's that? So you quickly jump off the edge, and then it slowly starts to creep back upward. What that shows is that a nucleon has the greatest mass when it's in the smallest atom of all, which is hydrogen. And as you move from hydrogen to helium, the mass per each nucleon quickly drops. What happens with that quick drop is that you're losing a lot of mass, and that means you're gaining a lot of energy. So as you lose mass, energy is released. But then as Tracy pointed out, the graph, after that quick drop, it starts to slowly creep back upward. And what that means is if you put two nuclei together, they now have a greater mass. What that means is the fusion in that case, you're losing energy. It's an uphill battle. To take like a uranium atom and put it together with another uranium atom, yeah, you might be able to cut them in half, but to put two uranium atoms together, this graph is showing that that's an uphill process. To fuse heavy nuclei together requires the input of energy. And that's a paradox. When you have light nuclei and you try to put them together, that releases energy. So when we talk about nuclear fusion is energy releasing only when you're talking about light nuclei.
This is so cool.
When we talked about nuclear fission, we're only talking about those really heavy elements. Nuclear fission applies only to like uranium, plutonium, and another uranium isotope. That's it. For nuclear fusion, if you want to get energy out of it, you got to go simple. You got to look to the simplest element, which is hydrogen. Take hydrogen, put it together with another hydrogen plus two neutrons, and you create helium. And as per this chart, you're losing mass, which means a lot of energy is being released.
So that's what's happening in the sun.
Yes. Hydrogen is being crunched together with hydrogen to form helium. Now, here's the deal. How are you going to get a positively charged proton next to another positively charged proton? They repel, do they not? How are you going to get them to come together like that? They don't want to. They're both positively charged. The magic tweezers and just squeeze them together? The closer they get together, the stronger the electrical force, the harder it becomes. It's a very difficult thing to do. To get those two hydrogen nuclei to fuse requires a lot of input of energy. So this is how you do it. You take one and you fire it really fast at the other. And they're moving toward each other so fast that their inertia overcomes that barrier and click. They bond. And as soon as they bond, the fusion happens, tons of energy are released. They stick together and you've got
helium.
Helium. Now, getting those hydrogen atoms moving really fast means what relative to temperature?
They're really hot.
Yeah, you got to get it really hot in order to have it fuse. And with a star, what you've got is gravity pulling all that mass together, compressing that mass together, like you mentioned in the last episode. When you compress, it heats up. And it's gravity that's compressing all that hydrogen and space together. And it's large enough such that at the core of that star, it is hot enough for the fusion to take place. Bam, you have the source of energy of all stars.
Cool.
Hot, actually.
That's very cool.
Yeah.
Very hot.
So from the hydrogen, you generate helium. And then, you get into the cool stuff about the life cycle of a star. And the star will put 3 helium atoms together to form carbon, right? And that's actually the fate of our star, the sun. What's the name of our star?
The sun.
Also known as Sol. And that's why it's the solar system.
Sol.
Sol, yeah. All right. And it creates carbon. That's the ultimate fate of our star. It'll turn into a big red giant and collapse into a white dwarf, which is a big ball of carbon. Fascinating stuff. From hydrogen, you beget helium. From helium, you beget carbon. Add another alpha particle. From carbon, you beget oxygen, which beget... And so you see that you are creating your elements of the periodic table through this thing called fusion, nuclear fusion. And this occurs within the stars.
So all the elements up until what you had said before is made by people, all of those are created in a star?
Yes, including the uranium, but not just any star. Here's the deal. If you look back at that graph, the lowest point of them all is where the nucleon has the least mass of all. And that is a special position held by the iron atom. With iron, you have this optimal distance within the nucleus such that the strong nuclear force is as strong as it can be. It's like if you want to be as small as possible in your nucleon, go to an iron atom and you will be as small as possible. Is to say, if you want to split an iron nucleus in half, good luck, because it's going to gain weight. If you want to fuse two iron atoms together, it's not going to work either, because it's now going to be, each nucleon is going to be heavier. Iron is the end point for any normal star, because as you fuse from hydrogen to helium, energy is released, right? There's your star. As you fuse hydrogen into carbon, energy is released, right? That's your star. You're still lighter than iron, and you're still going to be getting energy as you fuse heavier and heavier elements until you get to iron. Once you get to iron, the star can't generate anything more.
So where do elements heavier than iron come from?
A long time ago. You have occasionally these stars that are about 100 times more massive than ours. And when those stars reach the end of their life cycle, they collapse in one huge explosion where there is, for a moment, an abundance of energy. And from that abundance of energy, you can have fusion of elements heavier than iron. And from those brief moments, you create the gold in your ring, the platinum, the uranium, the thorium we hope to be using on this planet. All elements heavier than iron in the periodic table were created not in stars, but in supernova.
So that's the big explosion at the end of a star's life cycle.
Not just any star, but a star that has a mass of like 100 times more than ours. Ours will collapse into what's called a white dwarf. It won't undergo a supernova. It'll just collapse into a white dwarf, which is essentially a big ball of diamond. Yeah.
But for a very large star that is producing the iron, where does that iron go? It just goes into space. Space,
and it'll accrete and to form planets,
Okay.
Yeah. So look at the iron here on Earth. That came from star, likely a supernova. And I can guarantee you that elements heavier than iron did come from a supernova. And here's a fun fact. It turns out have a fair amount of gold here on this planet compared to other parts of the galaxy. Where other parts of the galaxy, there's gold is even much more rare. The reason we have as much gold as we do here on this planet is because we formed in an area of the Milky Way galaxy where there happened to be this supernova way before our time that created these heavier elements that accreted into our sun and its solar system.
That is definitely very cool.
Yeah.
Okay.
So nuclear fusion is what drives the stars. Any nuclear power plant is not doing fusion today. It's fission. And I guess this brings us back to Rocky Flats, because the types of bombs that they were working toward there were not fission-based bombs. They were what we call fusion-based bombs, working with hydrogen, right? So remember, it takes a lot of energy to squeeze two hydrogen atoms together.
Yeah.
Yeah. So turns out you can get to those really hot temperatures, not with gravity, but when they blew up the first fission bombs, they noted it was hotter than the sun inside those fission bombs. So they thought, why don't we do this? Take a little vial of hydrogen and surround it with a bunch of fission-type bombs, and then it'll be hot enough for that hydrogen to fuse into helium. Then we should get much more energy out of it. And they did. And that was in the 1950s. So in order to create those bombs that triggered the fusion of hydrogen, you had to have plutonium. That's what they made at Rocky Flats. Those plutonium buttons, what did they call them?
Yeah,
pucks.
they did.
Yeah, those pucks. At Rocky Flats, they were generating the plutonium that would be used for the fission bombs that would ignite the fusion bombs. That's scary.
Stop making bombs. Come on.
Yeah. But let's look on the bright side of things. Imagine you're around a campfire and you're getting all this warmth from the burning logs. The logs, they're releasing the energy they contain. So from where did the logs get this energy? Well, the log was part of a tree, right? So really, where did the tree get this energy from?
Well, from the sun.
Yeah, via photosynthesis, it collected this energy from the sun. So from where did the sun get this energy?
Well, the energy's coming from the fusion.
Nuclear fusion.
From the nuclear fusion.
So when you're feeling that warmth from a campfire, that energy is ultimately from the nuclear fusion within the sun. It's all connected. All right, so that wraps it up for this chapter on the atomic nucleus. And what's coming up in the next podcast, Tracy?
Is it an interview with Mike Lucas?
Mike Lucas.
Oh, that's going to be very cool.
A rocket engineer. And we'll be talking about the application of a lot of this science to the engineering world. All right.
Good chemistry to you.
Theme music by Zach Jeffrey, production assistance from Greg Simmons, and CPro Music. For show notes and more, please visit conceptualscience.com. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry.